Okay, so this is 6.4, polar coordinates. So what we're going to do here is we're going to introduce polar coordinates, learn some basics about them, do some graphing, and that's about it. We're not going to use polar coordinates too much in our class because it's towards the end of the semester, but they're super, super useful, especially in situations where there is rotating motion or something oscillating, because they're very useful for describing things which are symmetric about the origin, like rotating motion. Okay, so the good news is we pretty much, in a way, already know most of the stuff in that we talked about complex numbers. All right, so let's start there. So complex numbers, we said, can always be written as something plus something I, right? A plus bi. And when we plotted these, right, we have the x and y coordinate, we would plot a plus bi. If a were here and b were here, that would represent a plus bi. Okay, so that was the kind of standard form of complex numbers. There was also a trig form, where instead of writing in terms of a plus bi, instead of writing in terms of how many, well, again, in terms of thinking of it as, steps to the right, a steps to the right, and b steps up, if we think about it in trig form, what we would have is the same point would be described by r, which is this distance here, right, which is the length of the complex number, and theta, right? And in trig form, this would be a plus bi. In trig form, on the right-hand side, this would be cosine theta plus I sine theta. So from this perspective, you're describing the complex number in terms of theta and r instead of a and b. All right, so polar coordinates is a similar idea where, in a way, the regular Cartesian coordinates or rectangular coordinates that we normally use, right, like x comma y, or for example, let's say 1 comma 2, right, in rectangular or Cartesian coordinates, you just count the 1 is 1 step to the right, the 2 means 2 steps up, and that describes a point in the plane, right? But we can also think of, in a way, like a trig form, where we describe that same point using, instead of how many steps to the right, how many steps up or down or whatever, we describe it in terms of this angle theta here and this distance here, or that length there, r. All right. So in a way, you can see that if you understood kind of the transition from complex numbers in standard form to complex numbers in trig form, we're doing exactly the same thing here, except the transition from kind of rectangular coordinates, 1 comma 2 here, to what we're going to be calling polar coordinates, where you would be writing, instead of x equals 1, y equals 2, r equals something, and theta equals something. All right? So that whatever the angle is, again, theta is the angle with the positive x-axis, r is the distance to the origin. All right, so in a way, we're already comfortable with kind of transitioning between the two coordinate systems. So rectangular versus polar coordinates. Right. So if we did have rectangular coordinates, this 1 comma 2, let's do this example. 1 step here, 2 steps here. What is the polar coordinate version of it? And if you look at the online homework, when they want you to write something in polar coordinates, typically it's going to be written as r comma theta. All right. So the first coordinate is r. The second coordinate is theta. Okay, so how do you calculate these? Well, we know this is 1 comma 2. If we think about the Pythagorean theorem, right, this is this side length is 1, that side length is 2, And so instantaneously, r squared is equal to 1 squared plus 2 squared. And so r is equal to square root 1 squared plus 2 squared. All right. So square root 5 in this example. And theta, well, theta is right there. Angle with the x-axis. We can see that cosine theta is equal to adjacent over hypotenuse, 1 over that guy right there, square root 5, right? And sine of theta is equal to opposite over hypotenuse, 2 over square root 5. I guess I should write square root 5 here. Okay. All right, and using these two together allows me to solve for theta. Solve for theta. And again, we need to look at both of these because if you only look at one of them, for example, just cosine theta equals 1/5, there's two possibilities for theta, at least between 0 and 2 pi. And so you need the second one to identify exactly which of those two possibilities is the one that we actually want. Just like in transforming to trig form for complex numbers. All right, so you definitely need to consider both of these. Okay, an alternate kind of point of view is notice that tangent of theta is equal to opposite over adjacent, which is equal to 2. And so you can also try to get at least some information about theta by looking at the arctangent. Arctangent theta is equal to arctangent of 2, but notice this is only for theta between minus pi over 2 and pi over 2. Right, this only gives you theta between those two. So again, you're going to have to either notice, right, for example here 1 comma 2 does live between minus pi over 2 and pi over 2. So if we did use the arctangent function on our calculators, we would be getting the right answer. But if our, let's say our coordinates were minus 1 comma 2, right there, then the arctangent feature of our calculator would not be giving us the correct answer. All right, it would give me the guy down here, right? So you're going to have to adjust. So no matter how you do it, right, you're going to have to kind of think carefully about what your theta actually should be. So either you do it the way we've been doing complex numbers, right? Or you can very frequently, we use this arctangent thing if we know that our point that we're converting from lives here, right? Between where we have angle theta from minus pi over 2, right? So this angle here is minus, let me do this in a different color. This angle here is minus pi over 2. That angle here is pi over 2. So the arctangent function of your calculator will get you the right answer if your point lives in this region here. All right, so that's how you convert from between rectangular and polar. I guess I should write down some general formulas, right? So r squared is equal to x squared plus y squared, right? That was the equivalent in our example of r squared equals 1 squared plus 2 squared, right? And also we have cosine theta is equal to adjacent over hypotenuse. Sine theta is equal to opposite over hypotenuse, right? And again, the hypotenuse is r. Let me draw a general picture here. This is x, that's y, this is r, that's theta, all right? And so we're talking about this right triangle right there. And tangent theta is equal to y over x, right? So this tangent theta one, like the same example up here, is often useful because you don't actually have to calculate r, you just look at y over x. But again, you got to be careful that you're only looking in quadrant 1 or quadrant 4, or if you're looking in quadrant 2 and 3, you have to adjust to make sure you actually are getting the right theta. Okay, this guy right there and this guy right there, we often see them in the form, or they're often written in the form x equals r cos theta, and this second one is often kind of seen in the form y equals r sine theta. Right? And that's useful because these two together give you a way to convert the opposite direction if I tell you r is 6 and theta is 57 degrees, then automatically you can get x and y, right? And there's no problems in terms of calculators or anything like that here, because r cos theta is perfectly legitimate, r sine theta is perfectly legitimate. There's no issues of kind of using inverse trig functions, and you're not solving for anything like up here with using cos theta as 1 over root 5 and sine theta equals 2 over root 5. All right, so this means conversion is not too terrible. And again, we have been doing it for quite a while now with complex numbers. All right, so with that out of the way, right, now that we know we can easily or decently easily convert between rectangular and polar coordinates, let's take a look at why we actually care about polar coordinates. So the idea here is polar coordinates are able to describe certain things much easier than rectangular coordinates. So, for example, we have this r squared up here. We said r squared is equal to x squared plus y squared, right? Which was, again, just another way of stating the Pythagorean theorem in this setup here, right? But that tells us that, for example, what is a circle about the origin written in rectangular or Cartesian coordinates? It's x squared plus y squared equals the radius squared, right? Let's say 16. So this guy would have a radius of 4. So this is a circle of radius 4 about the origin. Right? It's about the origin because it's just x squared plus y squared. So notice if you want to describe this with just using polar coordinates, x squared plus y squared is r squared. So this is r squared. So this is just r squared equals 16. And we can say that's r equals 4, right? So what we're saying is we're considering all the points whose distance to the origin, right? That's what r is exactly 4. So the description in polar coordinates for a circle about the origin is super simple, r equals something. Whereas in rectangular coordinates, it was kind of complicated, right? So anytime you're working with circles about the origin, there's a good chance that polar coordinates is the right thing to work with, right? So if you're talking about something, again, moving in circular motion about an origin like this, right? In order to describe your motion, right, is just r equals a constant. You're always on the circle of radius, whatever, all right, 4 here. All right, that said, this is not necessarily simple when we're talking about circles not about the origin. If I have a circle, let's say up here like that, right, then its coordinates in rectangular coordinates, or its equation in rectangular coordinates would be x minus something. Let's say this is 3 comma 5. So x minus 3 squared plus y minus 5 squared is equal to the radius squared. Let's say the radius is 2, so this is 4. Right? So if you want to write this in polar coordinates, it's not necessarily going to be easy. It's certainly going to be easy, but it's not necessarily going to look nice, right? So if I convert this polar coordinates, up here we have, right, x equals r cos theta, y equals r sine theta, and you just use that. So the x minus 3 becomes r cos theta minus 3, whole thing squared. And then the y becomes r sine theta minus 5, whole thing squared, equals 4. Okay? So this guy is not so nice because if we actually try to do simplifications and stuff like that, this square and that square, when you multiply them out, you're going to get cross terms, and so you're still going to end up with a lot of r's and cosines and sines. So in this situation, it's not that nice. It's not as nice as this guy r equals 4, right? By the way, if you did do the same conversion, right? This conversion here, right? X squared plus y squared equals 16. It would be r cos theta whole thing squared plus r sine theta whole thing squared equals 16. And what would happen is you get r squared cos squared theta plus r squared sine squared theta is equal to 16. It's cos squared, sine squared, they both have an r, right? So this is going to be r squared cos squared theta plus sine squared theta equals 16. That's equal to 1. So we get r squared equals 16, which is r equals 4. All right. Okay. See, so this one works out nicely because under the square here, r cos theta, and under the square here, r sine theta, there's no extra terms. So when you do square them, you just end up with the cosine squared, sine squared. Whereas up here, right, when you square this, you're going to have to multiply this out, FOIL this out, and things will look very unpleasant. So circles about the origin, very nice. Other circles, not necessarily so nice, right? So the big advantage is when you're working with things in a way about the origin. Okay, so let's think a little bit more about pictures. Let's say we have r is equal to 3. That's a 3 there. Theta equals, let's say, pi. All right. So what position is that in terms of x and y? Well, r is 3. Your distance to the origin is 3. Your angle with respect to the positive x-axis is pi, so all the way around to here. Your distance is 3. So this distance from here to here should be 3. So this point right there. Okay. So of course you can, in this particular example, you can just literally see this is minus 3 comma 0. All right. Okay. Let's do another one. R equals 4, theta equals 270 degrees, just to have one in degrees. So this is going to be a distance of 4 from the origin, and we're going around 270 degrees. So that would be from here all the way to there, 270 degrees. And our distance to the origin is now 4. And that's our point right there. All right. Okay, now here's something interesting. We didn't really want to do this. We didn't want to do this with with complex numbers. But with polar coordinates occasionally, and we will be doing this later on in this lecture, looking at r as a negative number. So, well, okay, before we do that, what about r theta as a negative number? So that's perfectly legal. We've actually been kind of implicitly doing that quite a bit. So this guy right here, r equals 4, theta equals 270, is the same as r equals 4, theta equals minus 90 degrees. All right. Why is that? Well, distance of 4 from the origin, and minus 90 degrees means we take the positive x-axis and we go in the opposite direction, all right, the clockwise direction, which is not the usual one. So this would be minus 90 degrees, and distance of 4 to the origin, the exact same point. All right. Okay, so that's something that we notice about polar coordinates. You can have two different ways to represent the same point, right? 4 comma 270 degrees is the same as 4 comma minus 90 degrees. This is very different from the regular rectangular or Cartesian coordinates in that, right, x equals 1, y equals 2, there's no other way to describe that. All right, so that's in one way it's kind of convenient because, well, 270 degrees is kind of a pain, whereas minus 90 is a nice and simple number in a way, right? So sometimes it's nice to have kind of an easier way to describe the same point. On the other hand, it's a problem often because when you do have multiple ways to write the same thing, there's often a lot of room for confusion. For example, right, 1 over root 2 is the same as root 2 over 2, right? Two ways to write the same thing. If your answer is 1 over root 2, and the person who you're working with doing the homework, their answer is root 2. Yours answer is 1 over root 2. Their answer is root 2 over 2. Are they the same, right? They're not. They don't necessarily look the same. So it can cause confusion, right? So that's a bit of a drawback when you're working with polar coordinates. But even more than that, right? We describe these two guys in the same way, or this one point in the same way, using r equals 4, theta is equal to a positive number, and r equals 4, theta equals negative. But we also occasionally have to use r negative. So if I have r equals minus 4 and theta equals 90 degrees, how would I plot that one? So here, theta is 90 degrees, positive 90 degrees. So we're going 90 degrees counterclockwise from the positive x-axis. So that would be right here, like that, all right? But, okay, now, if r were positive, then no problem, right? We would just have our point somewhere on this positive x-axis here. So what happens when r is negative? What that means is instead of drawing right there on the positive x-axis, we draw on the opposite side, so the negative x-axis. All right. So instead of going here, r equals 4, we're going down here, r equals minus 4. Okay. So our point would still be the same point because this distance here would still be 4, right? So we're still talking about literally the same point in rectangular coordinates, the point 0, 4, but we've described it in yet another way. All right. So just remember, if you have r is negative, then wherever your angle tells you to go, you go in the opposite direction in a way. All right. So maybe I give another example here. So if I have r equals minus 3, theta equals 30 degrees, then this would be theta equals 30 degrees would be this angle here, right? So this is 30 degrees. But because r is negative, instead of our point being on this ray right here, it's actually in the opposite direction. So it's going to be back here. Okay. How far back here? A distance of 3. All right. So that's going to be our point instead of somewhere up here. All right. So as you can see, another way to describe the same point is 30 degrees plus 180 degrees all the way around there. So 150 degrees is like that. So an alternative description is r equals 3, theta equals 150 degrees. Okay, so these two guys are the same point. Typically, we don't really like to use negative r if we can avoid it. But like I said, in just a few minutes, we'll have an application where, in a way, it's kind of unavoidable. Negative degrees we often like to use just for the convenience, right? Minus 90 degrees is in a way more approachable than positive 270 degrees. All right. So let's talk a little bit about conversion. So we've already given the example of x squared plus y squared equals 16, converting very easily to r equals 4. So in general, if you have an equation in terms of x and y, it's pretty straightforward to convert them into r's and thetas, because again, x equals r cos theta and y equals r sine theta. So you can just directly do the conversion. And you'll see a few of these on your homework. One thing to try to notice is when an equation in terms of x and y is converted into something that's nice in terms of r and theta. So you'll notice, for example, something very simple in Cartesian coordinates, in rectangular coordinates, let's say just a line, y equals 3x plus 5. That doesn't really convert very nicely to polar coordinates, right? Y becomes r sine theta, and then x becomes r cos theta, right? This equation on the right is much more complicated than this equation on the left. So while you can, freely convert just using x equals r cos theta, y equals r sine theta, right? Doesn't mean that it's necessarily always going to be useful, right? So try to notice when the conversion actually gives you something nice on the other end. And if it does, that, very frequently means you want to work with polar coordinates, right? So like the case of, x squared plus y squared equals 16, converting into r equals 4. So here's another example. X, or let's say y equals 4x, right? So this one is also a line, but this line is through the origin, right? That line up there is not through the origin. So let's take a look at this conversion. So this converts to r sine theta equals 4 cos, for r cos theta. The r's cancel, and so we get sine theta is equal to 4 cos theta. And so this becomes tangent theta is equal to 4. And so here theta is equal to arctangent of 4. Right? So that's a nice expression. This arctangent of 4 is not so nice, but what you do notice that is nice is that this is just a constant on the right-hand side. So theta is just a constant, right? So a circle up here is described as r equals a constant. Down here, theta is a constant, describes a line through the origin. Okay, notice here we're allowed to have r negative, so this actually describes the entire line. So if this angle here, for example, is theta equals arctangent 4, right? Positive r would be up here, negative r would be the parts of the line down here. Okay, so arctangent 4 comma 10 would live right there. Arctangent 4 comma minus 5 would live over here, right? So we're still describing the whole line with theta equals constant. All right. So one thing to notice is in rectangular coordinates, when you have x as a constant, we're talking about vertical lines, right? So for example, this line here is maybe x equals 3. That line might be x equals 2. That line might be x equals 1, right? This line here is x equals 0, and so on, -1, -2, -3, right? Y equals constant, y equals 0 is this one. Y equals 1, 2, 3, -1, -2, -3. So when you look at one of the coordinates being constant, either x or y, in rectangular coordinates, you get a grid like this. In polar coordinates, when r is constant, right, when r is 1, when r is 0, you just get the origin. When r is 1, you get this. When r is 2, you get this. When r is 3, you get this, right? Circles about the origin, right? R equals 4, we already know, is a circle about the origin of radius 4, and so on. And what about theta? Well, when theta is constant, you get these guys here, right? So this is going to be kind of the description of kind of the breakdown of the plane in terms of polar coordinates over here versus rectangular coordinates over there. All right. Okay, by the way, another disadvantage of polar coordinates is that the origin is a problem because it's just r equals 0. Theta can be anything, right? So you have an infinite number of ways to describe that one point, the origin. So it is a bit of a problem sometimes. Just make sure you're aware of it. Okay, but what about conversions the other way? For example, what if I have an equation like r equals cos theta? This is a very standard one to look at. How do I convert that into rectangular coordinates? So you could technically use our equations. Again, from the picture, all the equations that you get from the picture, this is x, this is y, this is theta, this is r, right? But this particular guy is common enough that we remember this small kind of trick. If I have r equals cos theta, then I can multiply r on both sides. r squared is equal to r cos theta. And the reason we do that is because this is one thing that we should always be remembering when we work with polar coordinates. X equals r cos theta, y equals r sine theta, right? And so what I did by multiplying r on both sides was I, in a way, created the x right there, right? And so this is just x on the right-hand side. R squared on the left-hand side is really nice as well because it's just x squared plus y squared because it's the hypotenuse there. So x squared plus y squared is equal to x. All right. So this one actually turns out pretty nice. And in fact, if you kind of think about this even harder, this is x squared minus x plus y squared equals 0. And then if we complete the square, this is x squared minus 2 times 1/2 x plus 1/4 minus 1/4 plus y squared equals 0. The reason I did that is because these three go together as x minus 1/2, whole thing squared. And I got a minus 1/4 and a plus 1/2, y squared equals 0. I throw the 1/4 to the other side, x minus 1/2 squared plus y squared equals 1/4. And now we see this is actually just a circle of radius 1/2 about the point 1/2 comma 0. Okay, so this is a second example where the rectangular coordinates is a little bit complicated, but the polar coordinates is in a way kind of simple. All right. So you can do the same thing with r equals sine theta, right? And it's a good idea maybe just to do that same analysis, convert to rectangular coordinates and simplify as much as possible and try to recognize exactly what this object is geometrically. Of course, this example is one that's kind of set up perfectly for us to kind of convert from polar to rectangular coordinates, but that's not necessarily always going to be, things aren't necessarily always going to be so nice, right? Something like r equals cosine of 2 theta is not going to turn out so nice because even if I tried the same trick, I would get r squared equals r cosine of 2 theta like this, but r cosine of 2 theta doesn't become x because we've got this 2 theta instead of just theta, right? And x is equal to r cos theta. So even something, just slightly more complicated doesn't really convert very nicely into rectangular coordinates. However, you always can convert, right? Because we do have formulas that relate x and r. So, if we really, really wanted to, I guess we could do something like this. R is equal to cos squared theta minus sine squared theta. We could do this. R cubed is equal to r squared cos squared theta minus sine squared theta. That's multiplying r squared on both sides. And the reason I did that is so that I literally see a x squared minus, like that, x squared minus y squared on this side. And on that side, I'm going to get x squared plus y squared to the 3/2, right? Because r is square root x squared plus y squared. I cube that, and so I end up with 3/2 power, right? So this guy here is not really a very nice equation. Okay, so in a way, this indicates that if I did want to work with something like this up here, r equals cos 2 theta, it might be profitable to work with it in terms of whatever this geometric object is. It might be profitable to think of it in terms of work with it in terms of polar coordinates as opposed to rectangular coordinates, where this guy down here, very unpleasant because of the 3/2 right there. All right. Okay, so our next step is actually to visualize what something like this guy here looks like. All right, and we'll see that it's the procedure is a little complicated, but it's doable. And just imagine how you would graph this guy over here in rectangular coordinates, right? Not obvious at all. So let's think about this. So this next part is graphing, and the general feature is we're going to be graphing r equals and there's something in terms of theta. All right, so that's the typical idea here. Okay, And this kind of makes sense because what's happening, the way we're thinking of this is um, r as a function of theta. So, in a more mathematical way, instead of writing it like this, you might write r equals f of theta, right? So this description here is saying at every angle, so maybe at this angle right there, 10 degrees, I put in 10 degrees into my f and I get output some r, right? Let's say r become, when I do that for this function, the output is 10. So then I would mark that point there, all right? If I put in 20 degrees, right? So here's 20 degrees. Then I would put that into my function, get an output. Let's say r is only 5. Then I would mark that point right there, right? And what we can do is we can do this at every single angle, right? 30 degrees, let's say r is 2, right? Then 30 degrees is maybe something like that. Then we would be marking that point. All right. And so what happens is at every angle, we're marking a point. And of course, ultimately, we're connecting these in a way. And we would get a picture like that. All right. Okay, so this is in contrast to what we do in rectangular coordinates when if we have y equals f of x, right? What we're doing is at every x equals 1, we're marking the output y. At x equals 2, we're marking the output y. At x equals 3, we're marking the output y, right? At x equals 4, we're marking the output y. And so you end up, filling in like that, and you get a graph. So this is directly analogous to what we're going to be doing with r and theta, right? Thinking of theta as the input and r as the output. Okay, one thing to remember, we'll see this in just a second. If r is negative, if f of theta is a negative number, then instead of looking at, let's say, 10 degrees, we would be looking at the opposite side, okay? All right, let's do that right now. So let's look at the one that we just wrote down, r equals cosine of 2 theta. Let's try to graph this. All right, so the idea here, the way we really want to do this is to draw the picture in terms of, so let me say this. Ultimately, we want a picture in terms of x and y, all right? Because we're very comfortable kind of thinking in terms of x and y. So ultimately, for all of this section, our pictures want to be in terms of x and y, all right? So one way to do it is just to convert to x and y and use our graphing knowledge there to draw the picture. But what you can see up here, right, r equals cosine 2 theta, when we convert to x and y, it's something horrible that we have no idea what the picture looks like. Okay, so how do we draw? What we're going to do is we're going to draw it in 2 steps. The first step is to draw it in terms of r and theta. So in other words, an axis that's not x and y, but rather r as the input, theta as the input, r as the output. All right, again, that's kind of how we're thinking of this, right? R is equal to some function of theta. And then from that picture, we're going to draw the x and y picture, all right? So we're going to use the r theta picture to draw the xy picture. This is the most careful way to do this, and it's very useful because, as we'll see, trying to draw it straight out is not going to be necessarily so easy. I mean, even drawing it this way is a little complicated in that we have to be a little careful. All right, let me draw r equals cos 2 theta. Minus 1 is here, 1 is here, right? The amplitude is 1. Cosine 2 theta tells me that this guy is compressed by a factor of 2, right? This is why we did the graphing section. Cosine 2 theta has a period of pi, and this is just a regular cosine function compressed. So if I put pi, let me extend this a little bit, just so I have more space. So let's put pi here. Let's put 2 pi here. And let's draw cosine, right? It has a period of pi. But we want to draw more than that. We want to draw 0 to 2 pi, because what we're doing is we're going around, right? We're marking where r is at every theta as theta moves from 0 all the way around to 2 pi. Okay, so we want to draw the picture all the way to 2 pi, 0 to 2 pi. So I need to draw another one in this example, like that. All right. Okay, let me mark some of the interesting points. This one is pi over 2. This one is pi over 4. This one is 3 pi over 4, right? And maybe this is a little confusing. One way you can think of this is this first interval is pi over 4, then another pi over 4 gives me pi over 2, another pi over 4 gives me 3 pi over 4, another pi over 4 gives me pi. So all of these interesting marks are a distance of pi over 4 from each other. So this next one is 5 pi over 4. This next one is 6 pi over 4, which is 3 pi over 2. And this next one is 7 pi over 4. And then the last one is 8 pi over 4, which is 2 pi. All right. So what we're going to do is we're going to look at each of these kind of portions of these humps individually and draw our pictures that way. So for what I mean is this first hump, let me label it. So we're going to draw this portion first. All right, so let me call that 1. Okay, so this portion from 0 to pi over 4 represents, in terms of ultimately the picture that we want. Let me draw that here. This is x, this is y. Right? From 0 to pi over 4 up here represents the angle from 0 to pi over 4 in the x and y picture. I guess I lost a theta here. Okay, in the x and y picture. So we're going to be, this hump here, this hump number 1 represents the region in a way from 0 to pi over 4. So here's pi over 4, right? So we're going to be drawing the graph from here to here as theta moves from 0 to pi over 4. Okay? All right, so how does this work? Well, let's start at the very beginning, right there. When theta is 0, r is 1. All right? Theta is 0 means the x-axis, right? The angle with the x-axis is 0. The distance to the origin is r, and that should be 1. So this guy right there should be at 1. Okay? Actually, let me do this in the same color as up there. Right? So region 1 is labeled red. So this is going to be in red. So this is, we start out at a distance of 1. Now, as we move along the theta axis in the first picture from 0 to pi over 4, what's happening with our distance to the origin, which is r? It's starting at 1, and it's going all the way down to 0 by the time we get to pi over 4. So as our angle moves from 0 to pi over 4, the distance that our position is to the origin should go towards 0. All right? And ultimately, it looks something like this, right? As my angle gets bigger, I'm getting closer to the origin, right? And by the time I get to the angle of pi over 4, I should be at the origin, right? Because right there, pi over 4 comma 0, all right? So my picture should look something like that, right? Where I'm at the end here, I'm kind of tangent to the 45-degree dotted line, all right? And I'm moving in that direction. I'm putting this arrow to represent the arrow of moving in the positive theta direction, all right? Okay, so let me kind of zoom in and show this. So this here we said was 45, sorry, I'm using radians. This is pi over 4 radians, right? So if you take a look at this, if I draw just a couple more, right, here, this would represent an angle that's between 0 and pi over 4. And you can see my radius, the distance to the origin, is less than 1, right? And here's another one. My distance to the origin is even smaller. Here, my distance to the origin is even smaller. And as my angle gets bigger and bigger and bigger towards pi over 4, my distance to the origin is getting closer and closer and closer to 0. All right? So this guy here makes sense as a picture, as a rough picture for my graph. Okay? All right, let's do this next one in a different color. Oops. All right, So the next region we're going to do is from pi over 4 to pi over 2. All right. So from pi over 4 to pi over 2, in terms of theta, well, theta is going from pi over 4 to pi over 2. So that's from where we left off to pi over 2. Pi over 2 is 90 degrees, so that would be the vertical. All right. So we're technically drawing the portion of the graph that goes from here to there. Okay. All right. However, notice that r in this entire region from pi over 4 to pi over 2 has negative value, right? So what that means is instead of drawing the picture in the region that we're supposed to, we're going to be drawing on the opposite side. All right. What's the opposite side? Well, here's the opposite to pi over 4, right? The line that continues on the opposite end. The opposite to the positive y-axis is the negative y-axis. Okay. We're going to be starting at, we're supposed to be starting at pi over 4, and we're going to pi. So what we're actually going to be drawing is going from here to there. All right. Because again, r is negative. Okay. All right. So how does this work? So at pi over 4, r is equal to 0. Looking at our first graph, right? The theta r graph, right? At theta equals 0, pi over 4, r is 0. So we're at the origin, which is exactly where we left off. All right. As we move to pi over 2, r gets more and more negative until it hits -1 at pi over 2. Okay, so let me just represent that last endpoint right there. So at theta is pi over 2, r should be -1. So in other words, at theta equals pi over 2, let me erase these again. At theta equals pi over 2, in other words, this angle all the way to there, r should be -1. So instead of drawing in the positive y-axis, we draw in a negative y-axis a distance of 1. Okay, so we should end up down there. So we should be starting at 0 at the origin and ending at 0 comma -1. All right. Like I said, as we move from pi over 4 to pi, our angle gets our radius gets smaller and smaller. So we're going from here, and again we're going in this direction because let me do another example here. So this line, for example, would be represented by that one right there, right? So when we move from here to here, that would be moving from there to there in terms of -r, okay? All right, so we're going this way like this. When theta is pi over 4, right, we have r is 0, and then r gets bigger and bigger and bigger until when theta is pi over 2, we're there. All right, so the picture ultimately turns out like, that's terrible. Turns out like that. Let me draw this arrow here again. And then what we're doing is we're traveling in that direction. Okay, and again, the arrow represents what's going on as we travel from pi over 4 to pi over 2. Okay. All right, next. What we're doing next is pi over 2 to 3 pi over 4. All right. So what is that in terms of just theta? Pi over 2 is the vertical, right? Positive y-axis. And then 3 pi over 4 would be this angle right there, right? So what we're presumably drawing is this should be in that region right there. Okay. But again, what we see is that r is negative. So in actuality, we're going to be drawing on the opposite side, right? And again, this arrow right there goes from positive y-axis to 3 pi over 4. So here, it should go from the negative y-axis to the negative 3 pi over 4, right? So we should be traveling in that direction, okay? All right, what happens as we travel in that direction? Our radius goes from -1 to 0, right? So it should be from, on the opposite side, we should be here from 1. And then by the time we get to the green dotted line, we should be at 0, all right? So it should be something like that, and it's going to be tangent as we get there. Let me get rid of that arrow. Oh, disaster. Okay, there we go. Okay. So that's going to be, again, traveling from here to here, right? Which corresponds to traveling from there to there. All right. It's getting a little cluttered. Maybe let's do it over there, from there to there. And we're traveling in this direction. Okay. All right. This is getting a little messy, so let me just kind of draw an overall picture for now. Oh, I should label these, huh? This one, this region is 3, and this guy here is 3. This one was 2, and that guy was 2. All right. So so far, 1, 2, and 3 looks like this. So we're starting here. This was 1. This was 2. That was 3. Okay. 1, 2, 3. All right. So in a way, hopefully you kind of get the hang of the idea at this point. The next portion is from 3 pi over 4 to pi. So that's going to be, okay, let's use that. 3 pi over 4 to pi is this region right there, from here to there. And in terms of the xy plane, the xy picture, that's traveling from here to there. All right, 3 pi over 4 to pi. All right, pi is the is 180 degrees. Okay, let's see. Our theta graph is positive throughout that region. And so we're actually going to be drawing in this region here, right, as opposed to the opposite side. And what we're going to be doing is we're going to be going from r equals 0 until we get to r equals 1. R is increasing until it gets to r equals 1 at the angle pi. So 3 pi over 4 right there. And then we're getting big, r is getting bigger and bigger and bigger until we get to, that's a little too big, until we get to the angle pi, where it's a distance of 1 from the origin. Okay. All right, so at this point, what we just drew was this guy right there. That's number 4. Okay, so maybe a good idea right now is you can pause the video and try to finish it yourself, and see how that works out. If you get stuck, I'll be doing it right now. All right. Okay, so let's continue. So the next one is pi to 3 pi over 4. So that's represented by the region from here to there, right? Theta equals pi to theta equals 3 pi over 4. All right. Sorry, 5 pi over 4. 5 pi over 4. Okay. R is positive throughout this region, so we're actually going to be drawing inside that sector there, as opposed to the opposite side. We're starting at r equals 1, so actually exactly where we left off, of course. And then as we progress, as our angle gets bigger and bigger and bigger, our distance to the origin should be getting smaller and smaller and smaller. So like that. Okay. And in our, so this is number 1, 2, 3, 4, 5. And that's 5 here. And in terms of just a picture over here, that would be this guy right there. Okay. Next. Come on. Not a good color, sorry. Okay, so next we're doing 5 pi over 4 to 3 pi over 2. Segment 6. 5 pi over 4 is right there. 3 pi over 2 is the negative y-axis. So we're drawing this region right there. Okay. Okay, however, because our r from here to there is negative, we're not actually going to draw our picture here. We're going to draw it on the opposite side. Right? And again, you want to be careful about which exactly is the opposite side. Let's see. So this is this length right there is 5 pi over 4. So the opposite of that is that guy right there. The opposite of 3 pi over 2, which is the negative y, is the positive y. Okay, so if we're actually going to be drawing from there to there. All right. Okay, let's see. R is going from 0 to -1. So in other words, distance of 0, which is exactly where we left off as usual. And then by the time we hit the positive y-axis, right, 3 pi over 2, we should be at a distance of 1. So it should be something, something like that. All right, so this is 6. And we're ending up right there. And so this is drawing it here. That would be that portion right there, 6. Okay, and almost done. So we're just going to continue this kind of procedure until we finally finish, right? Until we get to the 2 pi. The next one is 3 pi over 2, which is the negative y-axis, until we get to 7 pi over 4, which is right there. Right? So we're presumably drawing from there to there. But because r is negative, we're not actually going to be drawing there. We're going to be drawing on the opposite end. So instead of, let me kind of shade it in this time. So instead of drawing in this area, we're drawing in this area. Okay. All right. R is going from -1 to 0. So in terms of distance to the origin, it's going from 1 to 0. We left off right there, right? That's exactly the correct distance. And we're going to 0 when we get to there. All right. This is number 7. And that's number 7. And that would be this guy right here. Okay. All right. Finally, our last one. We're going from running out of colors here. Let's do that. We're going from 7 pi over 4 to 2 pi. R is going from 0 to +1. It's all positive throughout that region. So we're actually going to be drawing where in a way we're supposed to. And that would be from here to back to here. So this way, in that direction. Okay. So let's see. We're going from 0 to 1. So 0 is the origin. And by the time we get to the positive x-axis, we should be at a distance of 1. So that guy right there. So this would be number 8. And in terms of just the picture by itself, we were here, and that's number 8. Okay. And what would happen if you kind of continued to draw this past 2 pi, you would just be repeating the portions that we already drew. All right. So there's no reason to kind of draw anymore. So altogether, right, if we drew it kind of in one smooth motion, it would look like this. So we started here. This was the first 0 to 45 degrees, and then to 90 degrees, and then to 135 degrees, and so on. Every 45 degrees, we're drawing one portion. And ultimately, it ends up like this, like a flower. All right, a little more symmetric than what I've drawn. I think our book probably calls this something like a 4-leaf rose or something like that. All right. Okay, we're not looking for super accuracy in our pictures. Something like this is good enough. But one thing you do want to kind of emphasize is, for example, here's the 45-degree line. As you come into it, right, to 0, you should be kind of tangent to that line. All right. Because that's supposed to represent what's happening at 45 degrees. All right. Hopefully that makes sense. Most of the homework problems are very, very similar to this in idea. Just do each of the portions of the graph kind of very, very carefully. All right, let's do another example. R equals cos theta. So graph. So this stuff is not necessarily the most useful material. You're probably not going to ever really need to graph these guys, but it's really good. These are really good exercises for, in a way, understanding polar coordinates and getting a good feel for how polar coordinates work. So these are maybe a good kind of, in a way, teaching tool for learning about polar coordinates, as opposed to necessarily a applicable tool that you might use in real life. In contrast to all the stuff we learned about complex numbers last time, where everything was super actually useful in real life. Okay, let's do this one. So this one is just r equals cos theta, so it's a little more simple, but I wanted to do the other one first because in some ways, our first example, r equals cosine 2 theta, was kind of simpler. So, or not simpler, but more straightforward. Because this one has an interesting feature here. So let's take a look at this. Let me do this one in degrees, just so we see kind of both points of view. Again, typically I like to do radians, and probably we should almost always be working with radians. But sometimes it's good to see examples in degrees now and then. All right, r equals cos theta. So this one, the r theta graph just looks as we normally expect. 360 degrees, 180, 180 degrees, 90 degrees, right there's 270 degrees. All right, so those are kind of the interesting landmarks. Here's my x and y graph. So when we look at kind of the structure of these humps, we want to draw them, this portion, and then we want to draw this portion, and then we want to draw that portion, and then we're going to be drawing that portion like that. All right, so that's how we're going to break up drawing this picture. But we'll see kind of something interesting here. All right, so let's start. From 0 degrees, I guess maybe even label that, 0 degrees to 90 degrees, that would mean drawing from here to here, right, as we travel from angle 0 to angle 90 degrees. What's happening is our distance to the origin should be starting at 1 and going down to 0. So when we hit 90 degrees, we should be at the origin, right? So starting here, distance of 1, right? Because this is just r equals cos theta. Cosine of 0 is 1. And then as we as our angle gets bigger and bigger and bigger, we should be getting closer and closer and closer to the origin. All right. And what's going to happen is it's going to look something like this. And when we hit 90 degrees, we should be at the origin. All right. So let me draw a couple things as we're getting closer and closer to 90 degrees. So if we're here, we should be pretty close to the origin. All right. So maybe let's say something like that. All right. Let me zoom this in. If our angle is even closer to 90 degrees, we should be even closer to the origin. So maybe something like that. All right. And as we get even closer to 90 degrees, we should be getting even closer to the origin. Oops, even closer to the origin. Okay, so ultimately what's going on is you can kind of see when we are at 90 degrees, we should be at the origin. And so we should be kind of getting tangent like that. All right. So our picture is going to be like this, where we're tangent to the positive y-axis at the origin. All right. So let me draw again another couple angles. Right. This angle here, we're right there. That's closer than 1. This angle here, we're right there. That's closer than the previous one. This angle there, we're even closer, and so on. As we get more and more vertical, we're getting closer and closer and closer to the origin. So this actually should be tangent right there, exactly tangent. Okay. Now, what happens as we travel from 90 degrees to 180 degrees? So that represents, let me erase all these lines just to make it less cluttered. So that's going to be 90 degrees to 180 is going to be this region here, right? But it's negative, so we're actually going to be drawing that way, right? And again, 90 to 180 is traveling in this direction in terms of theta. But because we're negative, we're actually starting at the negative y, so here, and traveling to the positive x as opposed to negative x, so that way, all right? So it's very easy to get confused as to what direction you should be moving. So, you know, here, 90 to 180, draw that one first. And then if it's negative, then you draw this arrow here, kind of in the opposite direction. Okay, so we're drawing down here in quadrant 4. And what's going on is we're starting at 0, right? Distance of 0 from the origin until we get to a distance of -1, distance of 1, right? So it's actually going to look like this. And we're tangent to 90 degrees until we get to there. All right. So this is 1. That's 2. That's 2. And this was 1. That was 2. All right. Okay. Now what happens if we continue? This next portion, 180 to 270, is supposed to be drawn there. But our r is negative, sorry. So we're actually going to be drawing there. And what happens is we're starting at r equals 1 and we're ending up at r equals 0. But these humps, again, are all symmetric to each other, right? So actually what's happening is you're traveling around the same circle. You're traveling around the same arc that you just traveled around in step 1. So step 3 is actually the same as step 1. And then now you can clearly see when I continue this, the last step, which should be here, is actually supposed to be drawn there because r is positive. And it's just going to repeat step 2, right? So it's going to be like that. Okay. So this picture here, actually, in a way, you already drew the whole picture as you went from 0 degrees to 180 degrees, right? So let me just draw the picture by itself as we progress, right? 0 degrees, bigger angle, 90 degrees, 90 degrees, 90 degrees to 180 degrees, all right? And then 180 degrees to 270 degrees is going around the second time. 270 degrees to 360 degrees is going around the second time down there. Okay. All right, so these are the kind of pictures that we're going to be drawing. There's a lot of different complicated shapes that can show up, but for our class, we're just going to do the ones which kind of either look like this or look like the previous example, like a flower in a way. But there's ones where you might end up with a picture like maybe a picture like this, right? Somewhat heart-like. They have names for these, lemniscates and stuff like that, cardioids. Let's not bother with those names. Like I said, we're not going to be using this very much since our class is almost over. And I don't think those terms are really important for you to know. But this process of graphing, I think, is important to understand just because it gives us a lot of practice in terms of, well, in terms of working the trig, right? The trig picture here, up here, and in terms of understanding how polar coordinates relate to um, uh, the trig picture up here. Okay. All right, so this picture stuff is probably the most difficult portion of this section. Everything, the kind of conversion stuff, just kind of use your knowledge of working with complex numbers in trig form, and hopefully, you'll have already been comfortable with that. By the way, just as a last note, we said that x and y coordinates we often write it 1 comma 3, r and theta. If you do write them in terms of parentheses, it'll be r is whatever 10, theta is 30 degrees, like that. Our book likes this, but oftentimes you'll see people just write r equals 10, theta equals 30 degrees, right? So there's no confusion, right? Because oftentimes people will omit the degrees, and then you might think it's 10 comma 30, like a Cartesian coordinate. So if you write r equals something, theta equals something else, there's no chance of confusion, all right? But also, if we think about what we talked about last time in terms of complex numbers, another way to write it is REI theta. So this guy, so here we're kind of thinking of polar coordinates in terms of complex numbers. And we said last time this guy represents r cos theta plus I sine theta, right? And that represents the point that's at an angle of theta and distance r, which is exactly the polar coordinates r comma theta. All right, so that's a nice compact way to write down a polar coordinate representation of a point where you're kind of referring to complex numbers. This is good for two-dimensional, for stuff in a plane, which is what we're focused on in our class. But of course, you can extend polar coordinates to 3 dimensions and so on. And in those cases, the kind of this complex number analogy doesn't work as well.